Advanced Math, Set 92, Probability of Either, and Notations for Permutations and Combinations. Okay, so the first thing we're going to talk about is mutually exclusive events. Mutually exclusive events are when one event occurs, the other event is excluded and cannot occur. So for example, if you're flipping a coin and you flip and you get heads, when you get heads, it's impossible to get tails at the same time. So the chance of getting heads is mutually exclusive from the chance of getting tails. Okay, same thing with a card. If we want to know the probability of getting a red card, if you draw a red card, that red card cannot also be considered a black card. So the red card cannot be black, so therefore it is mutually exclusive. Okay, so we're going to start with a problem involving an urn with marbles. So the total number of marbles in this scenario is 13. So we want to know the probability of getting red marbles. If I put my hand in, draw out one marble, the probability of getting a red marble is 3 out of 13. The probability of getting a blue marble would be 4 out of 13. And the probability of pulling out a white marble would be 6 out of 13. That's pretty basic probability. So now what we're going to look at is what is the probability of drawing a red or a blue marble. So we write that as P parentheses R or B. So the probability of a red or blue. So when we're talking about the word or, we take the two probabilities and we add them. So what is the probability of getting a red plus the probability of getting a blue? And that would be 3/13 plus 4/13. So the probability of getting a red or blue is 7/13. Okay, so now we're going to be talking about different kinds of problems, and it's one of the easiest ways to look at them is by looking at a Venn diagram. So if we took that previous problem and put it in a Venn diagram, we have 3 circles. One circle represents red, one circle represents blue, and the other circle represents white. And you will notice that in this diagram, none of the circles overlap because you can't pull out a marble in this scenario with a blue and a white marble. It's just either blue or either white or red. You don't get a red and blue marble, you don't get a red and white marble, and so on. So, drawing a red and white are mutually exclusive. There's no overlap. If you drew a red, it's not going to be white. So, the probability of getting red, again, is 3 out of 13. The probability of blue is 4 out of 13, and the probability of white is 6 out of 13. Okay, so we're going to learn some new terms for how to write the word or and how to write the word and. We'll start with or. So or is considered a union. It's considered everything that's possible. So when we're talking about unions, we use this symbol. It looks like a U but without a tail. It kind of looks like a cup. Okay? And when we use the word and is considered the intersection. And so when we talk about the intersection, it is this symbol. It's the upside down union symbol, otherwise known as the intersection. The way that you can remember intersection, well, the way that you can remember union is it looks like a U. One way to remember the symbol for intersection is that it looks like an A for and, but without the crossbar. So it's like if you're writing and, you don't use the crossbar. And then the other way that you can remember what is the reason for using the U symbol, think of a cup that holds everything. It includes everything. And then the intersection symbol includes only overlapping parts, like a street intersection. If we're talking about the intersection of a street, it's where 2 streets overlap. So it's those overlapping parts that are in the intersection. Okay, so when we talk about the probability of red or blue, we can also write it as the probability of red union blue. if we want to write the probability of red and blue, we write it as an intersection. The probability of red intersecting blue. So again, that's the intersect sign, and that is the union sign. So if you have mutually exclusive events, like the one in our Venn diagram, the probability of the red intersection blue is always going to be 0 for mutually exclusive events. If there's no overlap, there's no intersection. So if we're looking again at our diagram, the probability of red union blue, so all of the red and all of the red or all of the blue, we take all the red ones, all the blue ones, put them in a cup together, and we get 7 out of 13. If we're talking about the red and blue, that's the intersection part. We want to know what's the probability of getting a red and a blue when you put your hand in and draw out one marble. It's impossible to pull out one marble that is red and blue, so that is 0. There's no way to pick a marble that's both. Okay, so now we're going to talk about a Venn diagram where the circles do overlap. So this is an example where you have boys and redheads. The entire box would probably represent maybe like people in a particular room or something, where people that are the ones that are not in the circle could be people, like girls, it could be brunettes, it could be all sorts of different things. They don't fit in the category of boys, and they don't fit in the category of redheads. Now, when we look inside the circle, you can see that you have 7 boys and you have 4 redheads. But 2 of those are overlapping. You have 2 people who are boys and redheads, if that makes sense. So, there are 7 boys, there are 4 redheads, and we want to know the number of boys or redheads. So, if we're going to figure out the number of boys or redheads, we're going to take the number of boys, add it to the number of redheads, and then we have to take out the overlap because we've counted it twice. So we would do 7 plus 4, then take out 2 because we've counted it twice. And we get 9. So 9 people who are boys or redheads. And again, as I said earlier, they're not mutually exclusive. Okay, so let's look at this problem again. We have the total number of dots in this diagram is 13. The probability of getting a boy is 7 out of 13. The probability of getting a redhead is 4 out of 13. The probability of getting a boy or a redhead, like we said before, it's going to be 7 13 plus 4 13s. Then we have to take out the overlap, so minus 2 13ths, and we end up with 9 13ths. Now the probability of boy intersecting redheads, where those 2 circles overlap, there are 2 of them, and that's 2 13ths. So going back to the probability of B union R, we write it as probability of boys plus the probability of redheads minus the probability of boys intersecting redheads. Okay, a card is drawn from a full deck. What is the probability that the card is an ace or a black card? So, if we were going to draw a diagram of this, we have 2 circles and they do overlap. First of all, one circle represents all of the aces in the deck. The other circle would represent all of the black cards in the deck. We know if we're looking at the intersection, there are 2 cards in a deck of cards that are both aces and black. That would be the ace of spades and the ace of clubs. So there are 2 left in the intersection. Now, if we're talking about the rest of the black cards, if we're talking about all of the black cards, we know there are 26, including both of the black aces. So if there are 26 total and we take out those 2, we're left with 24. When we talk about aces, there are 4 aces in the deck. So there are 2 that are black, and then the other 2 are the red aces. So we've got 24 over on the right side and 2 over on the left side. Now what we're trying to figure out is what is the probability that the card is an ace or black. So, oh, and just another note, outside of the circle would be all of the red cards that are not aces, if that makes sense. Okay, so or. When we're talking about or, we're talking about a union. So we want the probability of A union B. So that means we would do the probability of A plus the probability of B minus the intersection. So in other words, we're going to take all the aces, we're going to take all of the black cards, and then we have to take out this middle part because we've counted it twice. So the probability of A is 4 out of 52. The probability of B is 26 out of 52. The probability of A intersecting B is 2 out of 52. So 450 seconds plus 26 50 seconds minus 250 seconds is 28 50 seconds. We can reduce that and get 14/26, and then finally 7/13. Okay, an urn contains 4 white balls and 3 black balls. 2 of the white balls are rough and 1 of the black balls is rough. What is the probability of drawing a ball that is either rough or white? So this one I'm going to explain without using a Venn diagram, and then we'll draw the Venn diagram at the end. So the first thing that we want to write down is what it is asking us. So we want to know the probability that it is rough or white. So the probability that is rough or white, we need to figure out the probability that it's rough plus the probability that it's white and subtract the intersection of rough and white. So the total number of balls in the urn is 7. The probability that it is rough, well, we can tell from reading the problem, it says 2 of the white are rough and 1 of the blacks is rough. So there's a total of 3 that are rough out of the 7. The probability that it's white, well, it says there are 4 white balls in the urn. So 4 out of 7 are white. And then the probability that it is rough and white, it says that 2 of the white balls are rough. So that's going to be 2 out of 7. So now we just put it all together. The probability that it's rough plus the probability that it's white minus the probability that it is rough and white. So we get 5/7. If we were to draw the Venn diagram of this, we would have 3 circles. 2 of the circles don't overlap because you can't have a white ball and a black ball overlapping. There are no circumstances where you pull out a white and a black ball at the same time. So we can label the white and the black, and then that third circle is rough, and it's going to overlap both the white and the black. So from our information, we can see that there are 2 of the white balls that are rough, so that means that 2 of them are not, and we know that 1 of the black one is rough. That means that there are 2 that are not. So that would be what the Venn diagram looks like. You don't have to do a Venn diagram. I just think it's helpful sometimes. But sometimes I think it could be more confusing. It just kind of depends on your taste. So now we're going to move on. We'll talk about notations for permutations and combinations. And really this is just kind of like to help your understanding. You already know about permutations and combinations. I think this lesson is really just to kind of make it so that you understand it in the context of what we were just talking about. So, if you remember, permutations are written in this form, and this is the equation for them, and then combinations are in this form, and this is the way that they are written. So, we'll start with permutations. The number of permutations for 7 things, taken 3 at a time, is, we would do 7 times 6 times 5. Now, the way that we write it as a permutation is we write 7p3, where we take 7 times 6 times 5 things. Now, this is not the way that it's written in the formula, so we're going to talk about how the formula came to be. So if I was going to remember, I can multiply by anything as long as I also divide by that same thing. So if I multiply the top and the bottom by 4 factorial, that's going to be the same thing as 7 times 6 times 5. I haven't really changed anything. So that's what I've gotten so far. Then I can reduce that because 7 times 6 times 5 and 4 factorial is 4 times 3 times 2 times 1. That's the same thing as 7 factorial. So I can just write that whole thing as 7 factorial over 4 factorial. Okay, and then we also know that 4 can be written as 7 minus 3. And that's important because that's what we're dealing with at the very beginning, is a 7 and a 3. So I'm just going to take that and replace the 4 with a 7 and a 3. So 7 factorial over 7 minus 3 factorial, and that looks like our equation. So NPR is going to be n factorial over n minus r factorial. That's where that equation comes from. Now, if we're talking about combinations are just slightly different. And combinations, for 7 things taken 3 at a time. Combinations, order doesn't matter. So when order doesn't matter, we're going to divide by those 3 places, 3 times 2 times 1, or 3 factorial. So we would write a combination as 7 factorial over 7 minus 3 factorial, which we just figured out in the last problem. And then we want to divide that by 3 factorial. So that's where the equation comes from. NCR equals n factorial over r factorial times n minus r factorial. And again, if it doesn't make sense, it's not a big deal because you have the equation and you know how to use the equation. This is just more how the equations came to be.